2.3, we're going to take a look at some other operations. So far the only operation that we have had has been the operation of complement. So we're saying A complement is everything in the universal set, not in A. So we have a few more that we're going to take a look at, 3 in fact today. The first one is called a set intersection. A set intersection is the set of all elements common to both sets. It is written as an upside down U, or you can kind of think of it looking kind of like a lowercase n. And in set notation, what this is the set of all x such that x is in A and x is in B. Now, if you think about the word we use in English for intersection, like the intersection of streets or the intersection of lines, that kind of intersection, it means exactly the same thing. It means where they cross. And where they cross would be the same thing, what they have in common. What do they share? Now, in terms of a Venn diagram, we can also draw an image of this visually. So if you draw a rectangle, it doesn't have to be a big one, just draw it off to the side. And draw 2 circles that overlap, like so. Okay, so the rectangle, as we've talked about before, is set U, the universal set. The circles are individually sets A and B. Okay, and then the intersection is the overlap. What do they have in common? The part they share. Okay. A set union is a little different. A union of sets is where the items are in one set or the other or both. So in a set union, it's actually a U between them. So that one's easy to remember. And this is the set of all x such that x is in A or x is in B. And you'll notice we don't write the phrase or both, but this or is not an exclusive or, it's an inclusive or. An inclusive or means either or both. Okay? So it could be in both. So this is kind of like what happens when you get married, right? So when my husband and I got married, right, everything that was his is now mine, and everything that was mine is now his. You get it all. Yeah? That's what a union, that's why we call it a union, right? We call it a union because you're merging everything together. At least that's the way that God intended it, is for you to merge everything together. So visually, with a Venn diagram, again, draw those circles that overlap inside. And we'll label them. This is the universal set, this is A, this is B. And the union is everything contained in either circle or in the overlapping part. So for the union, you get it all. So it reminds me of the movie Once Upon a Time called Yours, Mine, and Ours, right? This circle's yours, this circle's mine, and the overlap is ours, right? Think about blended families and things like that, okay? It's a union. The last set operation is called a relative difference. And a relative difference is the set of all elements in one set that are not in the other. So this feels kind of like complements. It doesn't work exactly the same way, but there are some similarities. And you see that it's called difference, and in fact we also are going to see a subtraction symbol show up for difference. So this is A minus B. This is the set of all x such that x is in A and x is not in B. Okay, so draw your two circles, overlapping. That's not going to work. All right. So we've got set A, we've got set B, we've got the universal set out here. So the complement or the difference, A minus B, is this piece where I've got the set A and it's the part that doesn't overlap set B. That would be A minus B. Okay, so A with B removed. And you could do the same thing of B with A removed. Kira? It's a curly brace. That's a B and then a curly brace. I was running out of space. Let me try and make it a little clearer. Is that better? It's a little bit small too. Sorry about that. Okay, any other questions about those three before we do an example? Okay, so we are going to do a blended family example actually. So we're going to consider Mary, single mom to one child, Mark, and Joe, single dad to two children, Jack and Jill. Mary and Joe get married, and together they have two children, Anne and Andy. If M is Mary's kids and J is Joe's kids, find and describe the following. So M intersect J. What would that be describing in our scenario? Kira? Yeah, so this is the kids they had together. And who are those kids in this actual description? It's Anne and Andy. So what would M union J be? All the kids, right? All the kids. I like that. So this is sort of, the family picture. Yeah? And this would be Mark, Jack, Jill, Anne, and Andy. And what would M minus J be describing? Yeah, the kids that are just Mary's. And who would those be? It'd just be Mark in this case. You could also say the kids she had before, right? She actually married Mark, or married Joe, whoever we had, Joe. All right, there's a couple of properties from numbers that actually apply also to sets, and that's what we're looking at next. These three properties, in fact, are commutativity, associativity, and distributive. So the commutativity of sets, intersection, and unions actually talk about the fact that if you had the union, well, I'll do intersection first. The intersection of A and B, it doesn't matter the order of that intersection. The intersection's the same thing. Right? When I talk about the intersection of Kickapoo and MacArthur, it doesn't matter if I say Kickapoo, MacArthur, or MacArthur and Kickapoo. It's the exact same place. Right? The order didn't matter. And union is the same thing. And if you think about how we shaded our diagrams, that makes sense. It doesn't matter if I shade one circle before the other circle, it all ends up getting shaded. Okay? Associativity also holds for our sets. So this is for all sets A and B. So the associativity property says the following. If you have A intersect B intersect C, I can regroup the intersections. A intersect B intersect C. And it works the same way for unions. A union B and then union C is the same as A union B union C. Now, I haven't drawn you pictures of what happens when you have a 3 circled Venn diagram, so that might be useful at this point just so that you can see as a reference point how I overlap these. So here is one of my sets. That's not what I meant to do with it. And 3 sets would do like this, okay? So if you can imagine taking the intersection of the top 2, right? They would intersect, for example, let me change the color pretty drastically, right here. That'd be the intersection of the top 2. And then if you intersected it, that little ellipse shape or whatever with the bottom circle, you'd end up with just this piece in the bottom. So no matter what order you do it in, you still end up with the dead center where they're all overlapping. And the same thing happens if you try to do union. If you do the union of the 2 circles at the top, you get everything in the 2 circles at the top, and then you join it with the circle in the bottom. You just throw in the extra stuff at the bottom. It doesn't matter what order you did it in. And so this works for all sets A, B, and C. The next one actually is the distribution of set intersection over set union. So this one actually talks about if you combine those notations together. So if you do A intersect B union C, that's the same as A intersect B union A intersect C. And again, this is for all sets A, B, and C. So there's a distribution across, just like distribution of multiplication over addition or over subtraction. And the most useful of all of these properties is actually the last one, the one we're about to hit. It's called the cardinal number property or cardinal number formula. And what it says is that the number of items in A union B is the number of items in set A plus the number of items in set B minus the number of items in set A intersect B. And when you look at it the first time, it feels a little bit counterintuitive to be subtracting. But let me show you from a Venn diagram perspective why it actually works. So just draw your 2 circles that overlap. So if I'm wanting to count everything in the union, we already drew what that looks like. I just shaded in both circles, right? Well, this is saying I could just count everything in set A. Let me label them. Well, if I counted everything in set A, I'll shade it in blue. I'd get all of this, right? This is set A. So that's all the stuff in set A. And then if I counted everything in set B, I'll do it in orange, I'd get everything right here. Did anybody notice what happened when I did that? I double counted the middle, right? I counted it when I counted the blue stuff, and I counted it when I counted the orange stuff. So it was counted twice. That's why you see in this formula the subtraction of the intersection off at the end. It's removing the double counting. So that's why we have to remove it once at the end so that we don't have that going on. And if you came back over and you did an example with Mary and, who are the people getting married? Mary and Joe. Mary and Joe, and you started thinking about it like this too. You could say, well, how many children does Mary have? And she'd tell you she has 3 children, right? And you said, how many children does Joe has? And he'd tell you he has 4 children, if you think biological children, this argument I'm talking about. But that does not mean that you would add Mary's 3 to Joe's 4, and all of a sudden you'd have 7 children, because you would have counted Ann and Andy twice. Are you with me? So that's why you're doing that removal at the end. All right, a Cartesian product is our last set operation in this description. And this is actually the set of all ordered pairs such that the first component comes from the first set, the second component comes from the second set. And you've seen this happen. Even the word Cartesian should sort of draw to your mind the Cartesian coordinate system, like the plane, right? The XY coordinate plane and all the ordered pairs XY. I'm going to create a different example for you just so you have another example to draw from. But all this is saying is that we have two ordered pair or two sets. So I'm going to make set A X, Y, Z. And I'm going to make set B the numbers 1 and 2. And the Cartesian product is actually, it looks like a multiplication symbol, X. And what it does is it takes pairs of things. So we're going to create an ordered pair. It's going to look like what we do when we do, algebra and write down a point, an XY pair for point. So you're going to take an item from set A, so that would be X, and you're going to pair it with an item from set B, that would be like the number 1. Or we could have paired the item X with the number 2. Or we could have paired the letter Y with the number 1, or the letter Y with the number 2, or the letter Z with the number 1, or Z with the number 2. And this is a collection now of ordered pairs. Now there's something that's very interesting to notice. What is the number of items that you get inside of the pairs? Like, how many pairs did we get? 6. This was 6, right? What was the number of items in set A? 3. And what was the number of items in set B? 2. Do you see a relationship between those 3 numbers? Yeah, the 3 times 2 is equal to 6, right? So that actually always works. Let me give myself a little bit more space. Give me just a sec. So it's always true that the number of items in the Cartesian product is equal to the number of items in set A times the number of items in set B. Now, that's just an argument talking about how many things there are, not what they are, right? This is just counting. We're just counting how many ended up being there. So if I count these 3 and I count these 2, 3 times 2 is equal to 6, and I get 6 items down here in the curly braces below. That's what that's talking about. Okay, so we're going to actually use some Venn diagrams now and see how we can use Venn diagrams to give us an idea of how these set operations work. So the first one is going to be a real simple one. And by simple, I just mean it's simple because it's only got 2 circles, okay? So there's going to be a 3-circle one right after it, and things get much more complicated when you have 3 versus 2 circles. So draw a rectangle and draw 2 circles. And then you're going to label them just like I've been doing all the way along with A, B, and the universal set U. Okay, pretty good so far? Okay, so here's the deal. This particular problem would be perfectly fine to do in different ways because it's pretty straightforward. But the more complicated they are, the more difficult it is to just reason which parts of this diagram it's really talking about. So I'm actually going to show you a method. This is not how I used to teach this, by the way. When I first started teaching these, I taught something very different. And I had a student come up to me once and say, look how my teacher did this somewhere, da-da-da-da-da. And I was like, oh, I think that's fantastic. So that's what I do now. Because it's really very nice. So what we're going to do is we're going to actually number the areas of the graph. And we're going to start with the part inside of set A. So this is region 1. The overlap is going to be region 2. The part in set B is going to be region 3. And then the part that's outside in the rectangle but not in the circles is region 4. All right, so like if you were working with a child and you were telling them to shade with as many different colors so that every color has its own region, there'd be 4 different colors you'd use, right? Yeah, there's 4 different regions here. And what we're going to do is we're going to actually take the pieces of information that are given to us here, and we're going to write down the regions that they correspond to. So A complement is one of the pieces of information that I'm supposed to be working with. What does A complement mean again? Yep, everything not in A. So what are the collection of numbers that are not in A? Are you sure? Just 3 and 4. Why is 2 not in my list? It's actually in circle A. I mean, it's in the overlap, right? So it's in circle A and B, but it's in circle A. So don't get to write it down. B complement is also in the problem. So what symbols or numbers are actually not in circle B? Yeah, 1 and 4, right? Everybody good so far? So this is kind of like when we're working with truth tables where we take the individual pieces first and we created a column for them, right? Now I'm taking those individual pieces and I'm listing the values, the numbers for those regions. And then I'm going to combine them with whatever symbols between them. In this case, what is that symbol between them? What does that symbol say? Is it union or intersection? It's union, right? It's a U. So this is the union. So when we're looking at a union, do we get the stuff they have in common or do we get everything combined? A union is everything combined. A union is the marriage, right? It's everything combined. So you literally look up at this list above and you write down everything combined, but you don't need to write things twice. So I'm going to write down 1, 3, and 4, but I don't need to write 4 twice because that's not necessary. It's already included. So the union of A complement and B complement is 1, 3, and 4. So what we've done over here is the work, right? We've done our work, we've shown our work, and I expect to see work on every single problem, even if you can reason it out in a different way, okay? Then I expect to see this work. And then the answer, the solution, is actually going back to your diagram and shading the appropriate regions that correspond to those numbers. So I need to shade region 1, region 3, and region 4. And when we get to the test, if you want markers, I have markers that I'll have and so forth. So this would be the solution to the problem. And then the other parts of the work to support. Everybody good? So we're going to practice another one with 3 circles now. Okay, draw a Venn diagram. Your Venn diagram needs to have as many circles as you have letters, distinct letters. So in this case, I have 3 circles. Starts to look like the Olympic rings, right? Yeah. All right, and our book doesn't get any more than 3, so 3 is plenty. ABC, sorry. 3 circles is all you'll ever draw. And the universal set U. Okay. I no longer have 4 regions, right? I could number 1 to 4 on the last diagram. I had 4 regions. How many do I have? You were counting that, Lydia. 8. That's right. I have 8 regions. That's exciting. Okay. So there's really not like a you have to number them this way. But the way that I always number mine is the same. I start with circle A and just go across. So this is 1, 2, 3. Then I go through the middle, 4, 5, 6. C is 7 in the bottom and 8 on the outside. But if you happen to number yours differently, it'll be okay. But we're going to do the same thing that we did before. Now, there are 3 sets that I'm comparing here, and there's some parentheses. So just like when you're working like an algebra, you work inside the parentheses first. Just like when we did truth tables, we worked inside the parentheses first. We're going to do that here too. So what is inside the parentheses? What sets? A and B. Now these aren't complements like the last one. They're actually A and B. So what values, what sections of the diagram are inside of circle A? 1, 2, 4, and 5. What values are inside set B? What numbers? 2, 3, 5, and 6. Everybody good so far? Okay, those are the individual pieces. And then they're going to be combined with what symbol? It's intersection this time, actually, right? It's the upside down U. So this is the intersection. So does intersection mean what they have in common, or does it mean you get everything? what they have in common. So I need to look back up here and figure out what do they have in common. So what do you see they have in common? 2 and 5. So the intersection is 2, 5. Okay, so we've done everything inside the set of parentheses, and now we're moving our way out from the side of the parentheses. So outside of the parentheses, then I have a C. That's the next set I have. So I'm going to put the set C next. What numbers are inside set C? 4, 5, 6, and 7, you bet. Okay. And we have 2 sets here now. I've got the set that's called A intersect B, and I've got the set that's called C. What symbol goes between those 2 sets? It's a union, and what does union mean? It means you get everything. So I get the 2, and I'll just go to 5, and I get the 4. I get another 5, but I don't need to write it again. And then I get a 6 and a 7. If it bothers you that they're not in number order, fabulous, change it, I don't care. So that's the work. And then I go back to the diagram and I shade it in. So don't forget the shading. You've got 2, 5, 4, 6, and 7. And this would be the visual that you get for that. Okay. So I'm in a dilemma, and I have been debating all class even how to answer the question at the end. Here's the dilemma, is that the test is supposed to be on Friday, and we still have half a section in group work. So I think here's what we're going to do. I actually already asked Taryn, you guys got an email, she's doing a review session for you on Thursday, and there's no way that that can be changed on the date. So the review session is going to still be Thursday, but I'm going to push the test back to Monday. It just doesn't make any sense to cram it when we have some time later on to work with. So unfortunately, your review session with Taryn will become before your review session with me, but I think you'd appreciate the weekend to do it more than to cram it in before then. So that's what I think I'm going to go with. Are you guys good with that? Okay, so this homework's not due on Wednesday. It's not going to be due till Friday, the homework for this, okay, because we're not finished with it. So we'll finish this section and we'll do the group work for this section on Wednesday. Sound good? All right, see you Wednesday.